Thank you very much for the introduction. Hello, everyone. It's a great honor to be here, and I would like to thank the organizers for involving me into this excellent workshop. I'm going to talk about our recent works on engineered polaritons in van der Waals materials, and these engineering methods include stacking, twisting, microstructuring, freestanding, and isotope heterostructuring. Previous speakers have done excellent jobs in introducing various types of van der Waals materials and their polaritons. What I want to quickly emphasize is the van der Waals engineering is really an important and versatile method to tailor and obtain or designed polaritonic nano-optical responses. And there are various methods to achieve these objectives as listed here. In this talk, I'm going to start with stacking, where we see our tunable and low-loss hyperbolic polaritons in graphene hexagonal boron nitride heterostructure and charge transfer polaritons in graphene MO3 heterostructure. Polaritons figures merit could be improved by freestanding, and by engineering the edge symmetry, we could achieve the mode conversion between different hyperbolic polaritons. In addition to stacking, one could do twisting to engineer the nanolight wavefront and also change the reflection phase in polaritonic microstructures. Also, there's a new materials engineering method called isotope heterostructuring, where we strategically position various isotopes to our engineer material properties, and we showcase that in our tailored phonopolaritons. All right, in this prototype of van der Waals heterostructure, probably the earliest van der Waals heterostructure of graphene on boron nitride, we could see the hybridization between plasma polaritons in graphene and hyperbolic phonopolaritons in boron nitride. The hybrid polaritons, they possess the combined volumes of each of the components. They always are confined at very small scales, similar as its component. However, these hybrid polaritons, they are low lossy because of contribution of boron nitride, and they're dynamically tunable because of our contribution of graphene. So in this heterostructure of graphene with MO3, that we see this very strong charge transfer effect, because these two materials, they have distinct work functions. And this charge transfer induces very high Fermi energy of graphene that blue shift the dispersion of phonopolaritons by a large degree. Stacking could also make design nanostructures in these freestanding samples. One could reduce the loss of propagating polaritons and also modulate their wavelengths, as shown here. In both hexagonal boron nitride and MO3, the reason is actually you are eliminating the substrate loss by removing the substrate, and also you could tune the polaritons by changing the environmental permittivity. So in addition to 1/3 improvement of the loss factor, one could also elongate or shorten the wavelengths of polaritons by freestanding the sample. Or in addition, stacking can also make terraces and steps. And where we study is actually the mode conversion between different hyperbolic branches. If you take a look at this simple edge, just a very simple edge, what you can see is only one oscillation period. So one period fringe shown here. But if you take a look at this stepped edge, you will see multiple fringes. And these polaritons, in addition to show oscillation fringes, they show the bits. This phenomenon was actually attributed to the mode conversion between different hyperbolic polaritons, because you break the symmetry at this stacked edge. And this phenomenon was shown more clearly by Fourier analysis, where you could see that from this simple edge, you only see the Fourier peaks from the first branch. But if you take a look at the stepped edge, you show very evident features, Fourier peaks of the higher momentum branches. And this was confirmed by our simulation that if you just in a simple edge case, your polaritons are always reflected at the input branch. So that means if you input the first branch, the polaritons, all of the energy get reflected into the first branch. If you input the second branch, all energy is going to reflect it as the second branch. That is the case for the simple edge, but if you use our step edge to break the symmetry at this edge, you could convert the first branch into different branches. So if you input the first branch, you're going to convert it and reflect it into our first branch and second branch, and you could have similar phenomena if you input the other branches. So by breaking this edge symmetry, you could achieve this mode conversion between different hyperbolic branches. All right, I believe that everyone in this conference has been convinced that in addition to stacking, one could also do twisting, and this is a very, very important strategy that you could utilize to engineer our quantum material properties and has been pioneered in this electronics, magnetics, and exciton physics. So the question we ask is whether we could see our twisting effect in polaritonic nano-optics responses. Well, if you take a look at these two pioneering polaritonic materials in van der Waals materials, hexagonal boron nitride and also graphene, it's probably difficult because if you take a look at these polaritons, they are propagating to all the directions. That means in plane, they are isotropic. So if you twist them, it's going to be difficult. Our MO3 with our extreme in-plane anisotropy may be a good candidate because polaritons in MO3 they are highly directional. They only propagate along fixed directions in this X shape. If you ask, what is the inspiration? Here it is. So you see that Auburn University is in the state of Alabama. So we just see this X shape every day, all right? So with this inspiration from our state flag, we did a simulation by stacking two MO3 slabs and then twist their relative rotation angles. In the simulation, we see that the nanolight wavefront could be engineered at the very broad twisting angle range. As you increase the twisting angle from 0 degree to 90 degree, you see that the polariton wavefront changed from an X shape to a tilted X shape to this so-called canalization has been mentioned several times in this conference. And if you further increase the twisting angle, it's going to go back to the closed shape. As you could see here in the simulation, we later on did the experiment that pretty much reproduce what the simulation predicts. We see this evolution of the X shape into canalization and into the closed shape of the polariton nanolight. Let me emphasize that this very specific angle is called polaritonic magic angle because if you take a look at the band structure or do this Fourier transform, or take a look at it at this our momentum space, this is actually flat band, so are pretty analogous to electronics our magic angle. All right, in addition to stacking and twisting, one could do microstructuring. What we studied is actually the reflection of polaritons, because reflection is very important. Reflection determines is a very fundamental parameter for light, and also without reflection, you won't be able to image these polaritons, although you have autocube equipment. All right. So reflection is actually going to be a complex number. It's not only just an absolute value. So it has the amplitude and phase. Amplitude of the reflection determines the intensity of your imaged fringes, and the phase of the reflection determines the position of your fringes. So no matter whether you have 3D polaritons in boron nitride two-dimensional polaritons in graphene or one-dimensional polaritons in various types of nanotubes. And no matter what they get published in Nature Science or maybe New York Times, they all have the same fixed reflection phase that is a quarter of pi. So this comes from the fundamental Gauss-Hanschen shift of these polariton modes. And the result is that your first interference maximum fringe is not at the edge. It's in the interior of your sample. And at the edge, it's always dark. We did this microstructuring and tried to alter the reflection phase of polaritons. As you increase the corner angle, one could see these polariton fringes move closer to the edge. And as your angle crosses 180 degrees, you see this at this edge, it becomes bright instead of dark fringes. So this clearly indicates that you have altered the reflection phase for polaritons. As one could see here, it's quite straightforward to understand. Refraction amplitude could change with your corner angle. Of course, you change how much energy could be reflected, but the refraction phase also changes with your corner angle. It increases and then has a pi shift. That is why you change from this dark into bright corners. These non-optical phenomena actually reveal the fundamental mass principle, because if you plot this reflection amplitude and phase into this polar coordinate, it shows that if you have a smooth transition of any complex function, complex number across the origin, you're going to have a pi jump of the phase if the transition is smooth. So that reveals this fundamental mass principle using non-optical phenomenon. All right, so recently we demonstrated the new materials engineering method called isotope heterostructuring. Isotopes are different atoms of the same element. They have the same number of protons, they have the same number of electrons, but they differ in the number of neutrons. Therefore, different isotopes will have different atomic masses and nuclear spins. And since these two parameters are very fundamental, our different isotopes are going to affect a broad range of material properties. So we demonstrate this new materials engineering method called isotope heterostructuring. Again, this motivation does not come from our state flag one more time, but comes from the fact that if you take a look at the current materials, take a look at these different isotopes, they are always distributed evenly or homogeneously in space. So we break this isotope homogeneity by strategically position different isotopes in heterostructures. And by varying the boron isotope in hexagonal boron nitride spatially, we could tune the dispersion of hyperbolic phonon polaritons, as you could see in these near-field images. These are the details that showing you by changing the composition and stacking of different isotopes. You could change the dispersions. These are 2 slab samples, 3 slab samples, 4 slab samples with different composition and stacking. And you could see our various energy momentum dispersions that can be engineered in these isotope heterostructures. So not only composition and stacking, you could control the thickness to tune the hyperbolic phonon polariton dispersion. If you take a look at the first 3 panels, they have exactly the same composition, same stacking. We just vary the thickness, and you will see the dispersions are totally different. And that is also the case for the 4-layer isotope heterostructures. The magic of the tuning of the new energy momentum dispersion in isotope heterostructures are the phase accumulation of phonon polaritons in these Faber-Parrot resonators. If you think about this isotope homogeneous structure, our phonon polaritons are always propagating a perfect zigzag. That means these phonon polaritons accumulate the propagating phase with a constant speed. Therefore, with this Fabry-Parrot resonance relation, different hyperbolic branches, they're indicated by different integral number, and they're perfectly evenly separated in this momentum space. However, if you build these isotope heterogeneous systems, you're going to have this banded zigzag propagation path. That means your phase accumulation speed will vary in different regimes. And in addition, you will have these phase jumps because of this evanescent tail and also the transmission through different isotopes at these isotope interfaces. So you will have the new isotope phase jumps. That actually depends strongly on this stacking composition and thickness of your isotope heterostructures that you built. Therefore, engineer the energy momentum of your hyperbolic phonon polaritons. All right? I'm happy that I stay on time. This is a summary showing that we demonstrated the engineering of polariton nanolight in various types of van der Waals materials, and van der Waals heterostructures. These are engineered hyperbolic, engineered polaritons will have exotic yet important properties that are not available naturally. I acknowledge the funding support and people who contributed to these works, and thank you very much for your attention.
Thank you very much for the wonderful talk. We have plenty of time for questions. Any questions from our audience? Oh, okay. Sorry.
Okay, thank you. You didn't mention over what length scale can you change the isotope? So if you want to do kind of isotopic patterning deterministically, what kind of length scale can you do?
Length scale?
Yeah.
Right now, okay, so these isotope heterostructures, the thickness are indicated here. And unfortunately, in plan, they're still monoisotopic, but we're trying to work on these in-plane isotope heterostructures to tune this propagation of the polaritons. No, we get this monoisotopic, isotopically pure crystals, and then we stack them into heterostructures.
Oh, okay.
Any more questions from our audience? Actually, I have a question. So you mentioned the isotope 1 and the isotope 2. If you stack those two different materials together and change the twist angle, what would you expect to see?
With isotopes?
Yes, different.
Okay, so for boron nitride, that polariton in plan is still isotropic. Okay. So, and this twisting effect of our MO3, they come from the electromagnetic interaction between these two twisted layers. So if you are electromagnetically isotropic in plan, I won't expect too much effect if you twist them using HBN. However, if you form these moire patterns at very specific small twisting angles, I would expect that at these different atomic locations, they will have different strengths, and then that may act as a new scatters for these propagating polaritons to change their propagation.
Okay.